Hey guys, this is a teardown of a Kodak Ektapro 4540 camera head. This 4540 camera system was the successor to the Ektapro 1000. That's this camera head and that processor back there. And these are significantly faster than that one. The Ektapro 1000 runs at about 1000 frames per second at 240 by 192, so that's about 46 megapixels per second. The 4540 runs at 256 by 256 at 4,500 frames per second. And that's about 300 megapixels per second, so a very substantial speed increase. And this system was released, I believe, in 1993. Now this is actually a very serious high-speed camera system. It's almost the 1000 is almost a toy compared to the 4540. This will support windowed modes down to very high frame rates, up to 40,500 at very small. I think it's a 64 by 64 window, but even at high resolutions like 256 by 128, it'll do 9,000 frames per second, which is nothing to scoff at. The images for this are absolutely huge, dwarfing the Ektapro 1000 system. They're very, very heavy. I think weigh about 12 pounds. They're all solid die-cast aluminum, very, very well built. I've got a few basic controls, something for gain control, gamma for the curve for display video, V-sync. I'm not sure if that's the monitor sync or actual high-speed sensor sync, and something connection for viewfinder. Sensor on the front is very huge. Apparently this has a 40 micron pixel size, which is absolutely massive compared to the 1 or 2 micron size on modern cell phone cameras, for example. On the back there's two giant circular connectors. This one looks like it's been broken by having the cable yanked to the side, because there's some very small cracks visible there. The other imager is a little bit, it's in better shape mechanically, but it has some rust, and the seller said it didn't work, so it's probably sitting under water or something. Okay, I wonder what's under this little back cover. Oh, DB connector, I wonder what that's for. It must be for some sort of debug operation or testing or something. Or maybe perhaps for a viewfinder that could be added on. You have to admit this thing looks absolutely badass with these giant cables coming off the back. Oh, look at that rat's nest. Looks like the connectors are divided up. One is just the image data, this one. Looks like it has 16 channels, the same as the old Ektapro 1000, but this the data rate is much higher in this one. To get the data rate this runs at, the 16 channels have to run at about 20 megahertz clock rate, as opposed to the about 3 megahertz in the old one. The other one seems to be primarily control signals and power. A lot of effort has gone into EMC suppression in this. There's little bits of EMC sealing gasket everywhere around the outside of this. I think this camera was also sold as the Photron Fast Cam in addition to the Kodak Ektapro. And I believe they also released a smaller imager head later on. This is obviously very large and cumbersome. Let's see if we can get all of these connectors out of here. Now, are these ones labeled? Looks like they're all labeled at least, so it won't be too bad. Definitely the pins on these ones are bent down from when the connector got pulled out. These ones, okay, 2 layers were needed there to get enough of them. That goes off to that little sideboard. And then in here we have a card cage with, looks like 4 plug-in cards. These two, I think, handle the video output because the output connectors are connected up to them. Looks like the one on the right is probably a power supply based on the inductors. The one on the left is probably some sort of a timing card. To get the card cage out, we're going to have to pull open the front of the camera. Here is the image sensor board. Oh, that's beautiful. Look at all those 16 analog connections over on this side. All the timing and power connections, and looks like under these shields we have a whole bunch of hybrid modules packed really, really tightly in there. Made in Japan. Just some NEC chips. Something is scribbled in Japanese onto the top of this. Let's get this thing apart. Okay, now we can get into the card cage. There's 2 analog processing boards. On these analog processing boards, the analog signals from the image sensor come in on the left, 8 channels. Looks like they go through some devices, they call them LPF, probably low-pass filters. And then there's 8 Sony A1310 CCD processing chips. These basically have sample and hold amplifiers, automatic gain control amplifier, and 2 different gamma correction curves as well as linear. So that's probably why there's that switch with the 3 different gamma ramps. They probably just found this chip had 3 of them, so they said, why don't we just put a switch on with that. A lot of times in product development, things like that will happen. Like you'll find a chip that does exactly what you want and it has this extra feature, and they figure, oh, hey, let's just add this feature as well because the chip supports this. And this could very well be a case here. And some other stuff. There's a bunch. It looks like 1 trim pot for each channel. A bunch of passives. So you see, these are a lot of these little SOT23 parts say U, so they're probably ICs like small op amps. It looks like they've had a provision to have a full shielding can over this on both sides, sort of like an RF circuit, but I guess they figured they didn't need it. These chips also have 75 ohm coax output drivers, which is important because the output of this goes onto these, which go out to the long cables off to the processor. And on the other side, this is double-sided load. There's some passives, looks like just RNC filters, 74 AC244, and some other stuff around the filters. This is the digital board. This primarily has a whole bunch of 7400 series logic on it, pretty much all the surface mount chips, as well as 6 GALs. Looks like they're lattice GAL 16 V8s. There's a crystal oscillator here, 24.948 megahertz. That's probably the pixel clock because the minimum pixel clock is something around 20 megahertz, so this gives some headroom for overhead times during the image sensor readout. There's usually blanking times when switching between lines and at the end of a frame. So 25 megahertz seems to be a reasonable clock rate for this. There's also this Murata part, which is probably an LC filter array, filter network. And there's these, which are this is just a power filter. This board is also double-sided load, a whole bunch more logic on the back. There are there's a bit of bodge work on this, but nothing major, not like any of the other, like the Starsight thermal camera or the motion scope. This one is very, very well built. This last board is just a whole bunch of linear regulators. They're pretty much all 7805, 7806, there's one 7905, and they have a lot of filtering. There's these inductor filters all over the place. A few trim pots. Wonder if they have adjustable voltages on this. The other side, not much. It's a bunch of traces, but definitely this gets very hot because the board around this area is discolored compared to over here. A few more things. They've removed some used to be resistors, just jumpered them. That's probably more filtering or perhaps current measurement stuff. And one little bodge right over there. There's a bunch of conflicting reports on whether this camera is actually a CCD camera or a NMOS camera, but I found this paper written by giving sort of an overview of this camera system, written by one of the lead designers. It clearly says it's an NMOS based camera, just like the older Ektapro 1000 series. It's a very interesting paper to read. I said go take a look at it. It explains in detail how the NMOS sensor works. It's actually significantly different from a CMOS sensor. It's more, it's actually closer in operation to that of a CCD than a conventional CMOS image sensor. Okay, there's the board. And there is the image sensor, made by Photron in Japan. Yeah, I believe this whole design is in Japan. It's mounted up on this little subboard. It looks like there's these odd little, very long sockets, and it looks like they're using the little sub PCB just as mechanical support. Relatively few pins. Obviously the ones all on this side are all the analog outputs, and these are all the drive signals. There's not all that much on this board. A couple of 74 HC series logic, some passive parts. This part appears to be an NEC UPD 65000 series gate array. This is sort of similar to the hard copy services FPGA vendors offer. It's basically a bunch of building blocks on a chip that are connected via user-specified metallized masks. This one doesn't match any devices directly listed in the datasheet, but it's somewhere between the 2000 and 3000 logic cell version. This is, I believe, built on a 2-micron process. This was a way to achieve relatively high density logic in a small package without having to pay the full development costs of an ASIC. Turns out these are not hybrid modules, but these are just little printed circuit boards with some sort of amplifiers and a whole bunch of filtering on them. There's 8 on this side, and strangely there's 9 on this side. You can see the designators go all the way from P-amp 0 or P-amp 1 up to P-amp 17, and the 16 of them drive the video output connectors here, and one of them, this last one, drives this 2-pin connector here that's wasn't connected to anything inside the camera. So I have to figure this is for some sort of debug or test operation for testing the image sensor. There appears to be one column at the row at the set of rows at the top that's masked off. Perhaps it's some sort of black reference used for testing. It's interesting to note that there are no custom hybrids in this. I would have thought that these amplifiers would be hybrids like we saw in the SP2000 system, just to make them smaller, but no, it looks like they're just these little PCBs with off-the-shelf parts. It looks like someone messed up with the pinouts or pin spacings on these, because it's matched up on the left, but on the right side the pins are misaligned, and they've bent the wires over to compensate. So somewhere in the mechanical design between these, someone messed up. Yeah, the only custom parts in this whole system are the image sensor and this gate array. What is that, sort of semi-custom? Everything else is just off-the-shelf parts. So even though the performance is going up in time over these compared to the previous generation system, they're using less and less custom parts. These probably consist of a FET amplifier on the bottom left, because the output of the image sensor is likely a very high impedance, so any capacitive loading would decrease the signal. And there's some big filter capacitors. I'm not sure if those are bypassing or just AC coupling. Some more various transistors or transistor arrays on the right. Here's a look at the image sensor under the microscope. It looks quite similar to the SP2000 system we were looking at before with the large output bus. Let's see if we can zoom in a little bit more. Yeah, there's on the right pixel array of 40 micrometer pixels, 16 channel parallel output bus. It looks like each output has either some sort of ESD protection or FET buffer of some sort. It's possible that for the high speed this runs at, this needs an additional buffering, unlike the other system. If we go down to the bottom, there's an area that's masked off. If you look closely, you can just see what appears to be the pixel array under that mask. What else do we have? There's that 17th output, which this is on the correct side of the chip that goes with that pin. So it seems that it connects to that the masked off area for some reason. Obviously some sort of a test. Bottom left pin there seems to be some sort of power, because there's lots of traces going off all over the place. You can see test patterns here that looks like these check the alignment between the different layers. Like there's AL1, 2, must be aluminum 1 and 2, TC, SD. You can't see it on the camera, but one of them says well. Must be for some sort of charge storage wells. More so they put one on each corner of the chip. It looks like they have some sort of a little vernier scale, because the one scale is slightly different from the other. That way they can check very precisely what the alignment is. Just judging from the pixels, which are 40 micrometers, the technology this runs at is probably something like 5 or 10 microns, so it's a very coarse technology. If you look, there's a bunch of what appear to be drivers for the groups of 16 rows of pixels, and from that document it gives some insights on how this works. Basically, this each one of these, you see this little tree going out to each group of 16. Each one of those individually at a time can be turned high. That basically selects that group of 16 rows of pixels to be read out. It looks like there's probably a demultiplexer in each of these little things. There's 4 lines that go off, and they probably use that as a binary code to select which of the 16 row selects are enabled. Also some various, looks like test things they put in, I don't know, transistors or test circuits that are unconnected to anything. There's some more test patterns up here. There's the sensor part number HE98256. Other little, I'm not sure what all, if someone can give insight on what all these little test patterns are, that would be interesting. And on the top we have, let me zoom out, what I think is the column select register. What this probably is a shift register that basically shifts a 1 from one side of the chip to the other, selecting which column to read out. And based on which row block select on the right is enabled, those particular those 16 pixels in that column, the voltages will be dumped onto the output bus and onto the outputs to be read out. And based on the windowing modes this supports, if you just look at the picture showing different modes, it looks like you can have windows, you can have a full 256 pixel width, which is probably the rightmost input. You can have 128 pixels width, which is would start over the second tap right in the center there, to start it at 64 up to I believe 192. But I think these are just ways to inject a 1 into a certain point in that shift register. The next one would be used for the smallest window mode, where it runs a 64 by 64 window in the center. And I'm not sure why they have other points to inject them later on. Maybe they had other windowing options to use parts, other sides of the chip that they just never implemented. This paper gives an excellent description of how this image sensor works. It says, the operation and control of one pixel within the sensor is illustrated in the figure below. A pixel consists of a MOS photocapacitor formed under gates G1 and G2. The gate G3 provides a DC potential barrier to isolate the photocapacitor from the N+ output bus. This bus runs the entire length of the row. During charge accumulation, G1 and G2 are held at a negative voltage, which creates a potential well beneath the photocapacitor electrodes. Photons may pass through this polysilicon material of G1 to create whole electron pairs. The electrons are swept out of the region. This is the opposite of how CCDs normally work. CCDs have a similar well that holds charge, but it holds electrons, and this sensor is opposite in that it stores positive charges or holes. The holes are captured in a depletion zone under the electrodes. The charge continues to integrate as photons create whole electron pairs until the cell is scanned during readout. And this basically implies the sensor uses a rolling shutter. It doesn't have any global way to reset the charge in the wells to 0. So basically, once you've read out a pixel, it immediately starts gaining charge again. And that also implies that the only exposure you can run is 1 over the frame rate, which is somewhat limiting. Modern CMOS sensors can run exposures that are completely variable from 1 over the frame rate to much shorter times. This readout cycle occurs when the G2 column electrode is pulsed to ground by the column scanner. That must be that shift register at the top of the image sensor we've seen there. First, G1 is grounded for the block scanned. This moves the photocharge under the G2 electrode in the selected block. Next, G2 is pulsed to ground. In the enabled block, charge is forced over the G3 barrier and onto the output bus. So that's the enabled block must be the groups of 16 rows that we saw being driven by the demux, or probably demux on the right side of the chip. This bus is a floating capacitor that refers to the output bus. The signal is detected as a change in voltage on the bus due to the injected photocharge. That's probably why they're using those CCD output amplifiers, the Sony chips we saw on the board earlier. Those allow you to do a sample of the bus, take a sample and hold at the output at 0 volts or without the charge applied. Then you apply the charge, it causes a slight change in voltage, and it amplifies that difference. In the blocks which are not enabled, the G2 electrode is pulsed. This moves the photocharge temporarily under the G1 capacitor electrode. After the charge has been sensed on the output bus, the bus is reset to a reference voltage. This is in preparation for reading the next pixel. G2 is returned to its negative level to begin accumulating charge. And it says the sensor has a full well of about 40,000 electrons. I wish companies would produce interesting, technically insightful papers like this today. Today they just produce a whole bunch of marketing BS. It would be very interesting to talk to this Chris Belch, who is technical director of Eastman Kodak. It would be interesting to get some insights into how this system was developed and how the technologies evolved over time. Anyway, I hope you found that teardown and look at the Kodak 4540 camera head interesting. I'm going to have to try to get a processor for this to actually get it running. I'm really interested in using this. This is actually quite a useful camera because it's actually quite fast. Stay tuned for the teardown of these other older Kodak systems. Anyway, hope you found that video interesting. Thanks for watching.